Good afternoon, everyone. My name is Atharva, and I'm from Trinity College, Dublin, Ireland. In this presentation, I'll be talking about integrating post-quantum cryptography into the XRP ledger. We'll start off by a quick overview about the XRP ledger and its current security algorithms. Then we'll address some threats faced by these security algorithms and how post-quantum cryptography could be used to solve them. Then we'll take a look at integrating CRYSTALS-Dilithium, which is a post-quantum algorithm, into the XRP ledger. And lastly, we'll be discussing throughput comparison and latency comparison of all the three algorithms. So XRPL is known for its various use cases due to its key features. It is cost efficient, it does transfers at high speed, is highly scalable, handles large volume of transactions. Its main use cases are decentralized finance, payment channels, tokenization of digital assets, and so on. Let's talk about XRPL's current signing algorithms, which it uses to perform cryptographic operations like key generation, method signing, and signature verification. XRPL currently has two key types, SECP256K1 and ED25519 both rooted in elliptic curve cryptography. For the case of SECP, it uses elliptic curve digital signature algorithm carried over an SECP256K1 curve, which is also an approach used by Bitcoin due to its robust security. On the other hand, ED25519 uses Edwards' digital signature algorithm carried over twisted Edwards curve, also known as curve 25519. Being a recently developed algorithm, it offers improved performance and security like resistance from side channel attacks. Although these algorithms are highly secure, they still face some threats which they could find overwhelming. These threats are from quantum computers. A quantum algorithm is a step-by-step computational procedure carried over a quantum computer, leveraging quantum phenomena like superposition, entanglement, and interference. The XRPL currently faces danger from two quantum algorithms. Shor algorithm is capable of solving elliptic curve digital logarithmic problems over the curve SECP and curve 25519 in polynomial time. It can also factor large integers, which could be a direct threat to modern encryption schemes like RSA. Grover's algorithm may not be a direct threat, but it can evaluate cryptographic hashes faster than traditional brute force methods, which would put, for example, a security of a 128-bit scheme to that of 64. Thereby potentially halving symmetry key encryptions and hash functions. To mitigate this threat, post-quantum cryptography refers to cryptographic methods designed for classical algorithms to withstand attacks from quantum algorithms. There are 6 different types of PQC cryptography. In our approach, we have used CRYSTALS-Dilithium, which is based on lattice-based cryptography. CRYSTALS-Dilithium is considered as a PQC standardized candidate by National Institute of Standards and Technology, NIST. It is based on Fiat-Schemmer with Aborts technique and leveraging it by using uniform sampling, which makes the lattice-based signatures compact and easier to implement. It is also built on Boyle and Gulbert scheme, which introduces a new technique which potentially halves the public key size by half. It depends on complex problems like short integer solutions and learning with errors. Now, if scalable quantum computers are built, like if the Q day occurs, these algorithms would be very much useful to withstand attacks from quantum computers. Now, let's talk about how we actually integrated CRYSTALS-Dilithium into the XRP ledger. So we have completed a tight integration of dilithium into the XRPL, which aligns with the style of SCCP and ED. Now, since the nature of dilithium is far more different than the traditional algorithms, some necessary changes had to be made to the core of the code base. Firstly, we observed a function which derives a public key from its respective secret key. Now, since this is not so straightforward in dilithium, we had to make a function which would perform deterministic key generation from a random seed using a pseudo-random number generator. Later on, we added a key type parameter, dilithium, along with the SecP and ED. One more crucial change which we did was we changed the static key array of 32 bytes to a dynamically sized buffer, which would take key size, which would accept any key size and would verify that once the respective function is called. For example, if we input a buffer of 32 bytes, and if we use cryptographic operations by dilithium, it would detect that that key size is not 2,528, so it will result in an error. Some of the ancillary changes are writing some build commands in the CMake list, similar to SCCP and ED, followed by introducing some libraries like dilithium2 and OpenSSL. With this, the build process is exactly the same as Ripple's traditional build process, but CRYSTALS-Dilithium will also be getting built alongside SCCP and ED. Now, let's take a look at throughput comparison and latency comparison between all the three algorithms over some key cryptographic operations and a full transaction process. On my left-hand side, we can see a throughput comparison between all the three algorithms. And from this, it is evident that dilithium is slower than the two algorithms, given its complexity. On the right side, we have a latency comparison. And from here, it is again evident that dilithium is far more slower than these traditional algorithms. But since this comparison is done in microseconds, it still is within the acceptable limits. If you want to check out more about this project, it's available on our website, appliedcrypto.com, where we have a detailed report of every single change we did at the code base, and it also contains some files which explains the changes in the code line by line. With that said, I would like to end my presentation here, and thanks so much for your attentive listening.